Hello everyone. In today's lesson, we're going to be looking at how to use derivatives to find maximum and minimum values. So to begin, let's actually define what an absolute or global minimum and maximum value is. So let C be a number on our domain D of a function f. So we have some function f, and C is some value on that domain D. FC is an absolute maximum value on f if our function fc is greater than or equal to f of x for all x in D. So that is to say, our fc is greater than or equal to all f of x, so for all x, on our domain D, or in D. This would be a global or absolute maximum. And then if we have that our function at that point C is less than or equal to every value of x, so for all x on D, this would be a global minimum. Now, what does this mean? Well, it just means that at this point, at some C, that if there is no f of x, which is greater than this value, then this would be our global maximum. Now, you'll notice that it is or equal to. That means that you could actually have more than one global max, right? For example, if I had like a sine wave, which went like this, then each of these would be a global max, because if I looked at this point right here, this might be C1 and this might be C2, these would both be a global maximum because they are larger than any other x value, but they're equal to each other, meaning that this is both a global and a local maximum. Same thing with minimum. If it is less than or equal to any value of f of x on that domain D, then it is a global minimum. So for example, if we have some graph, let's say it looks something like this. Something like this, right? So in this case, we have multiple maximums and minimums we could look at, right? So we have a maximum right here, and if you look, there's no value that is above this point, meaning that this would be a global or absolute maximum. And at this point here, if we were to consider, drawing a line across here, there's no value that is less than this, so this would be a global minimum. FC is a local minimum on our function f if our fc is greater than or equal to all f of x near c. So for example, if our c is this value, right, let's call this one c1, then near this c1, if there's no other value near it that is higher than it, then this would be a local minimum or maximum. If we had some c2 right here, then at this point around this value here, this would be a local minimum, right? There's nothing around this which is lower than this. Let's suppose you have some function that looks something like this. Then in this case, where would our local minimum maxima be? So for our local maximum, if we look at this point here, let's call this one C1. At this point nearby, there are no other values that are higher than this point. So this would be a local maximum. Similarly, if we look at this point here, there's no values nearby, near this C value, we'll call this one C2, that are higher than it. So this is also a local maximum. So at C1 and C2, we have a local maximum. Now, if we were to compare these with each other, though, if I were to look at this point and go off to the left and off to the right, you'll see that there are no other points that are greater than this. So this one would also be our global maximum. If we were to look at our minimum, we have some value here. Let's call this one C3. Where this nearby, there's no values that are less than this, so this would be a local minimum. Similarly, if we had C4, then at this point nearby, there's no values that are less than this, so this would also be a local minimum. So you might wonder, are either of these a global minimum? Well, of these two, this value is the lower point, so if I go off to the right, you'll see that there's no lower values, but if I go off to the left, I actually do have the fact that this function is going down towards negative infinity, meaning that both of these are local minimum, but they are not global minimum, because the whole point of our definition was that it has to be true for this c to be less than or equal to all values of x within our domain D. So what does this mean? Well, it means whenever you're looking for maximums and minimums, you're going to be looking for where are possible values where this might be true, right? We have something like this. And you also need to check the limits as you go off to infinity. What's happening with my function as I go off to negative infinity and what's happening with my function as I go off to positive infinity. Because in the end, I may have, when I find these specific maximums and minimums, I may have some behavior where, for example, like over here off towards infinity, I have it converging on some value L. So in this case, this is not going above this maximum. But as I go off towards negative infinity, this function went off down towards negative infinity, meaning that this local minimum would not be a global minimum because there are values that are less than this. So how do we actually find our local minimums and our local maximums? Well, if you look at what I drew here, every time I did this, I drew a line. And now, what do we know that we've learned recently to tell us what the slope of this point would be, which means we have a horizontal line? And that is, if we have some function that is continuous, if my derivative f prime of x is equal to 0, this is going to be a candidate, right? Because if you look at our slope of this graph that I drew, we have a positive slope, and then we have a negative slope. But where the slope is equal to 0, this is a candidate for a local minimum or maximum. When I get to here, I'm going downward, and then now I go upward over here. Again, I have a slope of 0. This one has a slope of 0, and this one has a slope of 0. So one of our candidates that we could look for is f prime of x equals to 0. The other thing we need to consider, let's actually write this down. These are going to be our critical values. And to find our critical values, these are going to be when f prime of x is equal to 0. That's where we have a horizontal slope, meaning that we could be going from upward slope to downward slope, meaning we have a maximum. We could be going from downward slope to upward slope, which means we have a minimum. Or we could be going from upward slope, hitting 0, and then going up. That would mean we have a saddle point, something like this. It's badly drawn, but you get the idea. Or it could be like this, going downward, hit a slope of 0, and then go back down. So this does not necessarily mean you have a maximum or minimum. It just means it's a candidate for maximum or minimum. We also could have where our derivative is does not exist. So let's consider an example of something like this. If I had the function f of x equals 1 over x. Here, our x cannot be equal to 0, right? Because at 0, it does not exist as we take the derivative as it approaches. Right? What's going to happen there? Well, as I try to plug in 0, what's happening? I don't know why I drew dotted lines. What's happening with this function? Well, as I approach 0 from the left, meaning I have negative values, right? Like 1 over negative 10, 1 over, and then what's happening is I'm getting smaller and smaller in my denominator, which means the value is getting bigger and bigger, but it's in a negative direction. And if I approach from the right side, it's going to look like this. So what happens at 0? Well, guess what? Now this means that this function does not have a global max or a global min because I have part of my function going off to negative infinity and part of my function going off to infinity, meaning that at does not exist. This would actually show that none of these possible candidates that I could have would be a global or an absolute maximum or minimum. So we do have to consider where a derivative does not exist. And then last, we do need to consider what is the behavior of our limits as x goes off to plus or minus infinity on our function, right? So what's happening with our function as we go off to infinity? We need to see what that behavior is to determine if we have a global or a local maximum minimum for any possibilities that we find based on our critical values. For our first example, let's consider the function f of x equals cosine of x. And we want to determine where our local minimum and maximum values are. So if we were to draw out what a cosine looks like, right, it's going to start at 1 when we're at x equals 0, and then it's going to go down, it's going to go to negative 1, and then it's going to go back up to positive 1, and it's going to repeat this over and over. And of course, it'll do the same thing if we go in the negative direction. So this means that our cosine of x is going to be greater than or equal to negative 1 and less than or equal to positive 1. Now, where are these values occurring, right? Because we know, just by looking at it graphically, that I'm going to have a maximum here, and a maximum here, and a maximum here, and then it's going to repeat over and over again. And I'm going to have a minimum here, and I'm going to have a minimum here, and again, it's going to repeat on forever. So let's just look to the right side, and we can also consider it's happening the same way on the left. So I'm going to start at 0, which you can actually think of this as 0 pi. And then this is going to be, so when it hits 0, this is going to be pi over 2. This point here is going to be at 2 pi over 2, which is just equal to 1 pi. This point here is going to be 3 pi over 2, and then this point here is going to be 4 pi over 2, which is just equal to 2 pi. That means that basically every 2 pi, this is going to be a maximum. So in this case, it's going to be cosine of 2 in pi, and this will be when it's equal to 1, right? So if I plug in 0 for n, I'm going to get cosine of 0, and that equals 1. If I plug in 1 for n, I'm going to get 2 times 1 is 2 pi. That's equal to 1. If I plug in 3 for n, I'm going to get 2 times 3 is 6, so 6 pi. So cosine of 6 pi will also be 1. Same thing if I go the other direction. Now for my local minimums, I need to have it where it's going to be every pi, so some odd number pi over 2. So in this case, it's going to be cosine of 2n plus 1 pi. And why is this? Well, because in this case, if I were to plug in 0, I'm going to get 2 times 0 is 0, so I'm going to get 1 pi. Cosine of pi is going to be equal to negative 1. If I were to plug in 1 for n, I would get 2 times 1 is 2, plus 1 is 3, so 3 pi. That would be when I come back around, and I'm going to be back down in the negative again. For our next example, let's describe the minimums and maximums for the function f of x equals x squared. So in this case, I'm going to draw a graph again where I have my xy axis, and what's going to happen as we plug in our values to this? Well, if I have x equals 0, I'm going to get 0. As I plug in 1, I get 1 because 1 squared is 1. If I plug in 2, I get 4. If I plug in 3, I get 9. So what's happening is I go off to the positive direction. It's going to increase faster and faster, exponentially. And of course, if I plug in negative values, because it's squared, it's going to do the same thing, but it's going to make it positive. So I plug in negative 1, I get positive 1. If I plug in negative 2, I get positive 4. So this is going to look like this. So kind of intuitively looking at this, what are my local and global minimums and maximums going to be? Well, it looks like I'm going to have a minimum at x equals 0, which is lower than any other value on this function, meaning that this is going to be a local minimum, but specifically it's going to be a global minimum. If I look at what's happening to the left and the right, this is going to go off towards infinity, meaning that I'm not actually going to have any maximums. So in this case, because x squared has to be greater than or equal to for all values where my function f of x is greater than or 0 for all x. This means that 0, or f of 0, is going to be my minimum. So this is going to be my absolute minimum. And it's also going to be a local minimum, right? Because again, remember, your local minimum just says that near this, there's no other values that are less than this. So it's a local minimum, but it's also an absolute minimum. Now, you might be wondering, why is this so important, local versus global? And a lot of times this is because when you're trying to do any sort of minimization or maximization problems, you're looking for that global minimum. And this is a big problem, especially when you're doing any sort of minimization or maximization algorithms, because a lot of times they can get stuck in a local minimum, right? So I might have something kind of like this, where it goes down, comes back up, and maybe this is the value that I actually want to find, but depending on the algorithm I use, maybe something like Newton-Raphson, if I start over here, right, I might come over here, and then I come over here, and I'm going to home in on this one. So while I will have found a minimum, it won't be the minimum that I want. And there's a lot of ways you can kind of deal with this, but this is an actual thing you might encounter if you get into anything like computer science or machine learning or anything like that. Because a lot of problems, you'll do something like gradient descent or some other method where you're trying to figure out what is this global minimum. And a lot of times, to save on computational power and time and effort, you might use something called like a greedy algorithm, in which case you're going to take the next step, which makes your answer better and better and better until it stops getting better. Meaning you might actually end up getting a local minimum or maximum instead of a global minimum or maximum. And then, of course, how do you deal with that? Well, it might be that you use something like Monte Carlo simulations, where maybe you start in different starting points and see what minimums do I end up in, and do I have one that seems to beat out the others? Could be other methods like that. But for now, let's just focus on the fact that, you know, if we have something like this, where nearby there's nothing below it, this is a local minimum. But of course, if I were to go outward, you'll see that there are in fact values that are less than it. If I look at this one, this is a local minimum also. But as I go out to left and right, there's nothing that is lower than it, meaning it is also a global minimum. What about if we had the function f of x equals x cubed. So just like before, if I were to quickly draw this, what is this going to look like? Well, as I plug in positive values, they're going to grow exponentially. So it's going to grow like this. As I plug in negative values, because it's now an odd function, this means that it will also stay negative. So therefore, it's going to look like this. So based on this, what is our local minimums and maximums? Well, in this case, if we were to find our derivative, which we'll talk about later when we talk about our derivative rules, and set this derivative equal to 0, we would get that we have a possible candidate right here, where the slope is equal to 0, where it's going from a decreasing change in slope to an increasing change in slope. But as we talked about, one of those candidates could also be saddle points, which is exactly what this is. So based on this function, as we take our limit, as x goes to negative infinity, this is going to go to negative infinity. And as we take our limit, as x goes to positive infinity on our function, this is going to go to infinity. So since infinity and negative infinity are not real numbers, this would mean that no local minimum or maximums exist on this function x cubed. For our fourth example, let's look at this graph here. So we have a function that we don't really know what the function is, but we can look at it visually and we can kind of determine what our local and absolute maximums and minimums would be. So we have the points A, B, C, D, and E. So looking at this, if we wanted to know what the local maxes are, it would be A, C, and E. If we want to look at what our local minimums would be, it would be B and D. Now, are any of these points higher than the others to be our global maximum? Well, in this case, it's kind of hard to tell because this isn't the best drawn image I've ever had. But in this case, C is just a little bit higher than E, meaning that it is our global maximum. For our minimums, we have between B and D. D is lower than any other value, therefore it is our global minimum. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.